Welcome back to day 2 of differential equations and slope fields. This one here is just like a kind of a review almost, just so we remember how to solve these things. Here they give us a differential equation and they give us a point, and they want you to like find the function that contains a point. That means the specific particular solution to this differential equation that has this point in it. So whenever they ask you to solve it, to find a function, you got to separate variables first. Always got to be your first step. So for this one, I would multiply both sides by y and then multiply both sides by dx. That would give me y dy equals negative x dx. Then I integrate both sides. I get y squared over 2. It's negative x squared over 2 plus c. And then remember, this is the point at which you should plug in what you're given to figure out what c is. Do that right now. Don't wait. Always better to do it now. So negative 4 for x and 3 for y. So 9/2 equals negative 16 over 2 plus c. That gives me c is 15 over 2. 25 over 2. Sorry, I don't know why I said 15. So I get y squared equals negative x squared plus 25 over 2. Y squared over 2, sorry. I multiply everything, this is all over 2. Multiply everything by 2 and I get y squared equals negative x squared plus 25. And so y is the square root of negative x squared plus 25. So that's fine, and that seems to work. But here's the thing, I mentioned this at the end of class, or when we were talking about this at some point in our last class, that like when you get done with these and you get your particular solution, you should always make sure that when you plug in the point, you get the right y. So when I plug in negative 4 for x in here, I should get 3 for y. And here's the thing. If I do negative 4 squared, that's 16, and negative 16 plus 25 is 9. So this is like the check step. So you're like y equals, oops, not y, 3. I plug in the x and the y I'm given. This is like a question mark. Is this true? Negative 4 squared plus 25. This is negative 16 plus 25, which is 9. And in this case, nope. Square root of 9, which is 3, so it works. But like if you run into issues when one of these numbers is negative sometimes, remember that the square root of both sides of this really gives me like, there's like a plus or minus here. And the way to determine whether it's plus or minus is to plug in the point. Like if this was negative 4 and negative 3, then this would have been negative the whole time, and you would have had to make this, this answer negative. So I might do another example like that in class. I just want to make sure you guys know that this thing could be negative. And that's why you have to check at the end. So differential equations are often used to solve problems that involve exponential growth. And that's because the growth of like living organisms usually increase at a rate proportional to the number of things in the population. Basically what that means is like if there's only 2 bunny rabbits, the population doesn't grow that fast. But if there's 100 bunny rabbits, the population grows really fast because there's way more bunny rabbits making little bunny rabbits. And that's true for populations of bunnies and bighorn sheep and human beings. And it's true for things like if you have like something that's decaying, like a radioactive element, and it's decaying, it decays at a rate proportional to the amount of stuff present. And that rate of change, if that's the case, and it'll be the case for a lot of these, this is the equation that we use to model that. It means that the derivative of y, where here like y is the amount of stuff present, the amount of things or stuff. So the change in that amount of stuff is proportional to the amount of stuff there is at that time. So the more stuff there is, the bigger the change is. And the K is like a constant that just is specific to the individual situation. And we often are tasked with finding that constant, or in order to solve the problem, you have to find the constant. So this is like the one application of differential equations that appears on the AP test. So we're going to talk about it in some detail. So growth and decay, that's what this concept is. You can also call it exponential growth because this always turns out to be exponential growth. So here is the kind of the general thing that we do here. We're going to do this kind of generic solving. It's like solve this equation for y, the general solution. So we know when we solve differential equations, the only way we know how to do it is separation of variables. So what I'm going to do to separate variables here is I'm going to divide both sides by y, then multiply both sides by dt. So I get y dy equals k dt. Nope, that's not right at all. I get dy over y equals k dt. Divide by y. And now that's step one. Now I integrate for step two, and I get the natural log of y is equal to the integral of k is a constant. The integral of a constant is the constant times the variable, which in this case is t, plus c. And now I integrate both sides, or I exponentiate. Remember, it says to find the general solution, so I'm not going to solve for c here. So now I say, well, if this thing equals this thing, then e to that thing equals e to that thing, which means y equals e to the kt plus c. Now, I don't want to freak anybody out here by doing some math from pre-calculus, but when I have something raised to a power and there's an addition in the power, I can write that like this. Because I know when I multiply exponents that have the same base, I add the powers, and I can do that backwards. Like this is going the other direction. There's a problem in the notes where we had e to the x minus y, and we wrote it as e to the x over e to the y. This is the same idea, but now instead of subtracting, it's adding, which means instead of dividing, it becomes multiplying. And this is the last thing that might freak you guys out a little bit, which is that this right here, e to the c, this is equal to c. I know that doesn't feel right, but like c is an arbitrary constant, which means, and e is also a constant. And if I raise a constant to the power of a constant, I just get another constant. This has to just be some number. So if this is e to the kt times e to the c, it's also like e to the kt times c. This is almost always written as y equals c e to the kt. So this is like your general formula for exponential growth. Y equals c times e to the kt. So any of the problems that have exponential growth in them are going to essentially use this equation. So kind of keep it in mind. And we're going to see that the constant has different meanings in different contexts. So this is like just kind of a summary of the law of exponential change, which says if y changes at a rate proportional to the amount present. So if the amount of something changes proportionally to how much of that something there is, then we would say that y equals c e to the kt, where k is some growth constant and c is some other constant. Usually for these problems, the c is the initial amount. So it's like however much you started with, and I can't spell apparently. Initial amount of stuff present, or the number of things present if we're talking about like sheep or bacteria or something. So usually I just written like this, y0 e to the kt. You can think about y when t is 0. this has to be y0, but really this is just a fact that when t is 0, this is just 1. So the amount present at time 0 is however much was present at time 0. So y0 is the initial value and k is a constant. So, and the k tells you if k is positive, then this represents growth, because that means this is going to get bigger as t gets bigger. And when k is less than 0, when k is negative, this represents decay. So you can think about growth as being like a population growing. Like you put a bunch of sheep in a pen and they make little baby sheep. I guess those are called lambs. And in that sense, the population grows. And if you have like bacteria in a petri dish and you put it in something that it can eat, then it'll grow as well. But if you have like a radioactive element and it's decaying, then over time there'll be less of it. That would be called exponential decay. So I'm thinking I want to do like one example, and then I'm going to be done with this for now, and we'll see how much that helps with our understanding. So this example, they just tell you that it grows according to its population. This is the this is our exact situation where we have this exponential growth equation. And we know from this page that if this is the growth situation, the derivative is equal to the amount times k, then this is how you find y. Like we've solved this already, so let's not solve it over and over again. Let's just remember that if this is a differential equation, then this is the solution. Okay, so we don't have to keep solving it every time. You could solve this, but you do it the same way we just did it. So let's not solve it again. So we know that y equals y0 e to the kt, where y0 is the amount at the beginning. And it says find the value of k. So here's what you do. This is almost like it's like a chemistry problem at this point. So I don't know what y0 is, and I don't know what y was, but it says every 10 years, the population doubles. Which means like whatever y0 was at the beginning, 10 years later, this should be twice as big as this one. So I can divide both sides by y0, and I get this. And what this tells me is that when t is 10, y is equal to 2 y0. When after 10 years, the new population is twice the original population. And if I use this information in this equation, I get 2y0 over y0 equals e to the 10k. And 2y0 over y0 is just 2. So 2 equals e to the 10k. And now I'm like, well, the question was, what is the value of k? So how do I get that out of the exponent? I take logs of both sides. This is that place where you're like, I wish I remembered logs from pre-cal. Well, I told you guys you were going to need it. Maybe you didn't believe me, but you do. So log of 2 equals a log of e to the 10k. I know that when I do, I can like rainbow this down. This thing comes down here. And I know, hopefully, you know that the natural log of e is equal to 1. The log of 2 is equal to 10k. Which means k is equal to natural log of 2 divided by 10, which is approximately, this is where you use the calculator. I mean, log 2 over 10 is an exact answer, but just for giggle, it's 0.0693-ish. 0.0693. So there you found this would be what I would call this number here, that k, would be called the growth constant or the decay constant, depending on whether it's growing or decaying. In this case, it looks like it's positive. So yeah, every 10 years it doubles, so the population is getting bigger. And so if I wanted to write this I have this equation here. I now know that K is 0.0693. So I could rewrite this if I wanted to. E to the 0.0693 T. Like this is like we found the growth constant for this, and then given any initial amount, I can tell you after how many years how much there is. So that's the point of this. That was kind of a lot, I know. We'll do more of this in class, I promise. But next class is slope fields and the beginning of this stuff. So enjoy.